Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to be going through section 7.4, Integration of Rational Functions by Partial Fractions. Okay, so kind of like what we did in 7.1, what we're going to introduce is a new way of dealing with integrals. Instead of dealing with U substitution in a very interesting way, what we're going to deal with is how do we deal with rational expressions, i.e. ratios or fractions of polynomials. What we're typically going to do is try to split this up into a list of simple fractions. Fractions such that the denominator only looks like a simple x plus a, x plus b, 3x plus c, anything like that. And the reason that we want to go with that is because any simple fraction like that, some constant over x plus something, that is just a natural log. So a over x plus a becomes a natural log of x plus a, b over x plus b becomes b natural log of x plus b. We're trying to get a list of natural logs, which are pretty simple to do with integration. This overall process of taking a complicated polynomial expression and simplifying it into very small bit-by-bit fractions is going to be what we call partial fraction decomposition. Now, it's not always the easiest thing to do, though, as you may expect. Taking a very complicated-looking fraction of polynomials and splitting up into individual pieces is not going to always be very simple. There are some that are kind of easy to do, and we'll have an example of one that doesn't take too much time. But a lot of these will take some time, so don't expect them to be very, very quick. You usually want to take your time, make sure you calculate everything carefully, and then work through it. Once you have the fraction set up, so once you have this part of the integral done, then it's easy. But getting there is the hard part. To help with that, I have basically a 5-step process that you're mainly going to follow in order to get to this. First, if we have p over q, just a simple rational function, we're going to check the degree of the numerator. If the degree of the numerator is larger than the degree of the denominator, then what we're going to do is use polynomial long division to simplify it down and separate out the rational expression. We'll actually have an example of this. So basically just check real quick that the numerator isn't bigger or equal to the denominator. If it is, then you can use polynomial long division to simplify some of it out. Second, what you want to do then, after you've done long division, is factor out q. You want to make it as simple as you can typically. You're usually looking for individual pieces like ax plus b, cx plus d, ex plus f, etc., etc., etc. You're looking for pretty small pieces. Sometimes you might not be able to get to that, but hopefully we can solve those fractions if necessary. Thirdly, you will set the rational expression equal to a series of fractions, and the number of fractions you'll have are going to be equal to the number of pieces that you have on the denominator, so the number of factors. For example, here I have a fraction that's already split up, and notice on the bottom I have 1, 2, 3 pieces. That means I'm going to have 1, 2, 3 fractions, one fraction for each of those pieces. The degree on the numerator is going to be equal to 1 less than the degree of the bottom. So I have x plus 1 on the bottom. That means on the top I'm going to have the highest degree of x to the 0 power, since the highest degree I have on the bottom is x to the 1. Likewise, I have x squared on the second one, so that means the highest degree I'm going to have is an x, and then I'm going to keep decreasing terms polynomial until I have a constant. 3x plus 7, highest degree I have is a 1, so the highest degree I have up here is going to be, again, a 0. So that's how we're going to be setting up those fractions. Then, once you have all that ready, the trick is going to be to try to find what A, B, C, and D are, or these capital unknown values. In order to do that, what we're going to do is multiply the numerator by the product of the other denominators. So that means what I'm going to do for this example I have up here, I'm going to see this a over x plus 1, and what I'm going to do is I'm going to multiply a by the other denominators. So x squared minus 2 and 3x plus 7. And then I'm going to do that for all the other pieces. So the bx plus c, I'm going to multiply that by x plus 1 and 3x plus 7, so the other denominators. Overall, this is simulating cross multiplication. If I were to take the denominator on the other side and multiply it to everything on the other side, then that would essentially cancel out the x plus 1 there, and so I would only have the other two pieces multiplying by a. So that's going to simulate our cross multiplication. When we have that, then we're going to have just a simple equation. We're going to have all the things on top of the right side with the unknown constants, and we're going to have that equal to the original numerator, my 5x equal minus 12. Then I should be able to either use a series or system of equations, or I can use matrices to try to solve A, B, C, and D. Notice that in this 5-step process, I don't talk about taking the integral at all. I'm more talking about how to set up those fractions and how to evaluate what each of the unknown values are. That's the main trick. Once you have the fractions, they're easy. They're all going to be natural logs or maybe some other special cases, inverse functions. So this general process will help you solve the problems, and we're going to go through some examples of these. A couple special cases you do need to keep in mind, though. If you do have a repeated factor, for example, x plus 2 to the third, because that happened 3 times, that can very often occur. If it does, what that means is that we're going to have still an individual fraction to represent each of those x plus 2's, but each fraction is going to be increasing in the exponent. So x plus 2 to the second, x plus 2 to the third, all the way up to whatever the highest degree is. So that's to the third, so likewise I only have 3 fractions. I also have 5x plus 6 to the second power, so that means I'm going to have 5x plus 6 and 5x plus 6 to the second power. So 1 for each of them. The difference, though, is when you do have repeated fractions, the numerator is still going to be defined by whatever the original one was. So if you notice, x plus 2 is my original with no exponent, and the numerator is 1 degree less. Likewise, for all the repeats, I'm also only going to have 1 degree less. So I'm going to keep it as b and c. I'm not going to keep this as bx plus c and cx squared, etc. I don't need to worry about the exponent on the repeated factors. So that's a special case. We usually want that anyway because it makes it easier to solve. Lastly, although a difference of squares can be factored, a difference of squares is equal to x minus a, x plus a. Even though you could do that, you can't do an addition of 2 squares. But there is a very famous, I will say, integral that you often will see. That's the integral of dx over x squared plus a squared. That will give you 1 over a arctan of x over a plus c. We talked about this before back in 7.1, that this is going to be an integral you're going to need to know, and it will come into play even more now and more moving forward. So if you haven't already gotten this integral down, please do so as soon as possible. Alright, so that's a big blurb in terms of what all we're doing here. Let's go through some examples so you can see how this is done. First, we have the integral of 2x squared minus 3x plus 2 over x plus 5 dx. Alright, well in this case, we notice based on my step-by-step process, I look at the degrees of the top and the bottom. I see the degree on top is x squared, the highest, and the degree on the bottom is x to the 1 power. So that means the degree on the numerator is actually bigger. Therefore, we're going to approach this using long division first. So let's show how this would be done. Okay, so I'm dividing by x plus 5, so that's going to be outside of my long division. On the inside is the polynomial on top, 2x squared minus 3x plus 2. My goal is to see how many times x plus 5 fits into this expression. That way I can get some amount of that outside of the fraction, and so that the numerator on top is just a simple degree less of x plus 5, so there's just a simple constant. To do that, what you pay attention to is the leading term every time. So my leading term is x, and now my leading term on the other side is 2x squared. I need to think about what I need to multiply 2x or x by so I get 2x squared, and what I need to multiply x by is 2x. X times 2x will give me 2x squared. And since I multiplied this entire expression by that, I likewise need to multiply 5 by 2x, which will give me plus 10x. Doing that will allow me to subtract this away, just like if I were to do long division for whole numbers. 2x squared minus 2x squared should hopefully eliminate that term. That's the goal. And now I have minus 3x minus a 10x will give me negative 13x. And then I could drop down this plus 2. Again, I see my leading terms. I see the original x I have and the minus 13x. So what I need to multiply x by is a negative 13. So that I get, just like I got here, I get negative 13x. And then negative 13 times 5 will give me 10 times 5 is 50. 3 times 5 is 15, so that's 65. I'm going to subtract that expression away from negative 13x plus 2. Like before, that will allow me to eliminate these 13x's. And I get 2 minus a negative 65, so that's plus 65, so that's overall 67. Now, 67 has a degree less than the expression I was dealing with. Therefore, I am done using long division, and I can rewrite this integral. I can say that this integral is going to be equal to the result of my long division, 2x minus 13. And then I also have left over, I have a little bit of that 67. So I have plus 67, which is from right here, over my original denominator of x plus 5 dx. This integral now is very easily solved. The integral of 2x is going to give me x squared. The integral of minus 13 will give me minus 13x. And then 67 over x plus 5 will give me 67 natural log of x plus 5. And then a plus c because I don't have any bounds on my integral. All right. If you want to work with how I got natural log out of this, you could just do a u substitution on just this bit, calling u to be x plus 5. Du would just be dx. And so you get 67 over u dx. And that's what allows you to get natural log here. So that's all we're looking for. Notice that case I didn't need to do any partial fraction decomposition because it already was in simplest terms after I did the long division. So I don't always need to do the entire process. For these next few, we're going to have to do that. All right, so example 2, we again look at my integral. I have x plus 13 over x squared minus 2x minus 3. I notice the degree on top is 1, the degree on the bottom is 2. So that means that the numerator is smaller, so I don't need to do long division here. What I do need to do, though, is split up this integral. So I need to split up the denominator. I see x squared minus 2x minus 3. That is factorable. X times x will give me x squared. Two numbers that multiply to make negative 3 would be negative 3 and 1, or negative 1 and 3. But since I see the middle has a higher negative value, that means I'm going to have a negative 3 and a positive 1. That way negative 3 plus 1 adds up to negative 2. Then what I'm going to try to do, this integral, my goal is to split this up into a over x minus 3 and b over x plus 1 dx. That's my overall goal, is to split that up appropriately. All right, now in order to do that, again, what I'm going to do is I'm going to take each of the top terms, and what I'm going to do is multiply them by the other denominators. So I'm going to take a, multiply that by x plus 1. I'm going to take b and multiply that by x minus 3. This is going to equal x plus 13, which is the other numerator. Again, basically what I did was cross multiplication. If I were to do this cross multiplication, I would take x minus 3 times x plus 1 and multiply that by both a and b. However, when I multiply by a, that means the x minus 3 would cancel, so I'd only have x plus 1. If I multiply by b, the x plus 1 will cancel, so I only have x minus 3. That's why this is a little bit of a faster process. But now I need to solve this. My favorite way of solving this is to reorder it so I have something that looks like this other side on the right here, this x plus 13. So I want to find some amounts of a and some constant and set those equal. So I see ax plus 1, that will give me ax plus a plus b times x minus 3 will give me bx minus 3b. Group those with x's and with the constants, and what I get is a plus b x. And what I also have is a minus 3b make up a constant. That will equal my x plus 13. So therefore now I can set up fractions so that the constant terms are equal to each other. I have a 1 in front of this x, and a plus b in front of this x. So that means a plus b equals 1. And I have a 13 constant, and this is my constant term. So that means I also know a minus 3b equals 13. Now, if I put these together appropriately, I can add or subtract them as a system of equations, or if you would like to use this as a matrix, you may, doing 1, 1, 1, 1, negative 3, and 13, and solving this matrix. That also works. I'm just going to do a system of equations here. And what I'm going to do is simply subtract these. So let's even subtract them right here. If I subtract them, that'll cancel out a's, and I get b minus negative 3b will give me 4b, equals 1 minus 13 will give me negative 12. Divide by 4, and I get b equals negative 3. With that in mind, I can plug that into either of the previous equations. I'll plug into the first one because it looks the simplest. A plus b, where b is a negative 3, equals 1. Add 3, and I get a equals 4. So now I solve for my two unknowns. Therefore, what I'm working with now then is the integral of a, where a is 4, over x minus 3. And plus b, where b is negative 3, so we'll say minus 3 over x plus 1 dx. These are now easily solvable. This is going to be 4 natural log of x minus 3 minus 3 natural log of x plus 1. And then plus c for an unknown constant term. Okay. So hopefully you see how that functions. This one overall isn't too bad because it only split up into 2 fractions, so that means we only needed to solve for 2 unknowns, and they were relatively simple unknowns. Okay. So with that said, let's dive into one that's a little bit more complex. Notice, though, before we move on, most of the work, this, was making the fractions simple. Once we had the fractions, like here, the integral was super easy. Didn't really take much time. That's how these generally go. The work is really the setup. I have the next 2 examples on their own pages because they may take a little bit longer. Okay, here we have from 2 to 3, 3x minus 5x squared, all over 3x minus 1 and x minus 1 squared. In this case, the integral, the fraction itself, is already split up, so this should be pretty simple to set up as a series of fractions. We want this to be set up as, I see the first term is 3x minus 1. 1 degree less of that is just a constant. Plus, I see x minus 1 squared, which is a repeated term, so I'm going to have a single term of that, x minus 1. And then since that's a 1 power, 1 degree less would be a constant. And I'm going to keep that same thing in mind with the next repeat of it, so x minus 1 up to the second power, dx. So here we have 3 numbers we're going to solve for. And again, what we're going to do is multiply each of the numerators by the other denominators. So what that means is that I'm going to multiply a by really x minus 1 squared, because that's what I would get from here. So I'll say a times x minus 1 squared. If I multiply b, I'm going to multiply b by 3x minus 1 and one term of x minus 1. And I'm going to multiply c by just 3x minus 1. Again, we're thinking about it in terms of cross-multiplying this stuff over. So when I would multiply b by that, one of the x minus 1 terms will cancel, but I still have one left over. And this I want to set equal to the original numerator of 3x minus 5x squared. All right, so let's do some manipulation. All right, up here we have x squared minus 2x plus 1. That's what this turns out to be. Here we get 3x times x is 3x squared. 3x minus 1 is minus 3x, minus another 1x gives you minus 4x, and then a plus 1. And then we still have this 3x minus 1 here. So then what I want to do is group by the terms. So I want to have some amounts of x squared. I also want to have some amounts of x, and I want to have some amounts of a constant to equal, if I put this in normal order, minus 5x squared plus 3x, and then no constant. Looking at what I have above, for x squared, I see an x squared here is going to multiply by an a, and a 3x squared is going to multiply by a b. So that means what I have is a single a, and I have 3b to give me x squared. For a single x term, I see a minus 2x here, so likewise that's going to give me a minus 2a, because that would multiply the a back in, and then I'd factor the x out. I have a minus 4x, so that means I'm going to have a minus 4b. And I have a 3x here, so that's going to give me a plus 3c. And lastly, for my constant terms, I have a 1, so that's going to give me an a 1 here, so that's going to give me a b, and a minus 1, so that's going to give me a minus c. So a plus b minus c. All right, so that's how I grouped all the terms together. I kind of skipped the step of multiplying it out and then factoring because this would be the same process. All right, now we can set up three equations. We have our coefficients. We have a plus 3b should equal this coefficient here. So a plus 3b is going to equal negative 5. Likewise, I have my next coefficient. I have negative 2a minus 4b plus 3c. That's going to equal the coefficient for x, which is a 3. Let's see if I can align this up. And I have my constant terms of a plus b minus c. That's going to equal a 0. Okay. Now, how to deal with this. Again, you could set this up as matrices if you want to deal with matrices if you're comfortable with those. However, if I deal with this as a system of equations, I see an a plus 3b. So I see that I have just two unknowns. So if I make these other two fractions such that c goes away, I can make another set of equations with a and b only, and then solve for either a or b from there. So that's what I'm going to do. I'm going to take the last two. I'm going to take minus 2a minus 4b plus 3c equals 3. And what I'm going to do is I'm going to add 3 times a plus b minus c equals 0. The reason I add 3 is because my goal is to eliminate this plus 3c. I see that I have a minus c, so if I multiply that by 3, I get 3c minus c, so those will cancel. However, resulting from this, I get minus 2a plus 3a will give me a singular a. Minus 4b plus 3b will give me a minus b. And 3 plus a 3 times 0, which is 0, I just get 3 overall. So I get a minus b equals 3. That means I can take my original a plus 3b equals negative 5 from my original set, and I can subtract away this new equation of a minus b equals 3 to isolate a and be left with just b. This will give me a minus a is 0. 3b minus negative b will give me 4b. And negative 5 minus 3 will give me negative 8. Therefore, dividing by 2, we get that b equals negative 2. So I'm going to collect that over here for now. So b equals negative 2. Let's have all three set. So a equals, b equals, c equals. These are what I'm going to need to know. Right now we know b equals negative 2. With that in mind, we can solve for a using either of the previous equations. I like this a minus b we got. But to be careful, I'm going to use the original equation we had of a plus 3b equals negative 5, and I'm going to plug in negative 2. However, it shouldn't matter which one you do. 3 times negative 2 will give you negative 6, and adding 6 to the other side should give you a equals 1. So that's what we get for a. And lastly, we just need to solve for c, and I'll use the last equation of the three that I had originally because that looks the easiest. It shouldn't matter which one you do, though. Once you get one variable, the other one should fall into place. A plus b minus c. We know that a is 1. We know that b is minus 2. We have minus c left over. 1 minus 2 will give me negative 1 minus c equals 0. Add 1 will give me a 1 on this side, but then I get rid of that negative by multiplying negative, and I get c equals negative 1. So those are my three values for a, b, and c. Notice that it takes some work, but that's fine. Once I have all the work done, then it just takes a little bit to simplify the rest of it out. Now I have the original function, which was 3x minus 5x squared over 3x minus 1 times x minus 1 squared dx. I now have this as the integral of 2 to 3. The bounds haven't changed. The first one was a, which was 1 over 3x minus 1. And then b, which is negative 2, so minus 2 over x minus 1. And then c, which is a minus 1 as well, so we get minus 1 over x minus 1 quantity squared dx. Okay. Now, depending on how you want to go about this, it's really up to you. The first one shouldn't be too bad. The first one should give you 1/3 natural log of 3x minus 1. And the next one will give you minus 2. That 1/3 is coming from the chain rule for 3x, by the way. Minus 2 natural log of x minus 1. But then this last one has an extra term on it. What you can really say is that this is the same as 1 over u squared, where u is x minus 1 and du is just dx. So then the integral of that will be minus 1 over u, where u is x minus 1. And this is going to be integrated from 2 to 3. Plugging in those bounds, we get 1/3 natural log of 3 times 3 minus 1, so that's 9 minus 1 is 8. Minus 2 natural log of 3 minus 1 is 2. minus 1 over 3 minus 1, so that gives me 1 over 2. Minus, if I plug in 2 now, I get 1/3. Natural log of 3 times 2 is 6, minus 1 is 5. Minus 2, natural log of 2 minus 1 is 1, so that's actually 0. Natural log of 1 is 0. And then when I put in 2 here, I get 1 over 2 minus 1, which is 1, so I get a minus 1. Okay, now you can keep all these natural logs separate. However, I do see this natural log of 8. Natural log of 8 is the same as natural log of 2 to the third, which I can pull that 3 out and cancel out there. And then minus 2 natural log of 2. I also have a minus 1/3 natural log of 5. And I have a minus 1/2 and a plus 1, so that will give me overall plus 1/2. So then I can combine these appropriately. I get negative, like this is a positive 1 natural log of 2, minus 2 natural log of 2, so minus natural log of 2, minus 1/3 natural log of 5, plus 1/2. All right. Now, that should be good enough. However, you can continue to simplify this more if you so please. For example, you can say that this is negative. These are both natural logs, we can factor a negative out and then add them, which actually multiplies the inside. So negative natural log of 2 times 5 to the 1/3 power plus 1/2, and that negative can go in and move that all to the bottom, so you can also say natural log of 1 over 2 times 5 to the 1/3 plus 1/2. That's going even further. However, this should be just fine. Reduce it down into pretty few terms. Okay. So again, most of the work was up here, was reducing down and trying to find the fractions. After that, once I found that, doing the integral wasn't too bad. I just took a little bit extra work to make it into a simple kind of function. Yeah. Okay. One more, and this is going to introduce another concept with this. If we look at again, focus on the degrees first. The degree on top is x, the degree on the bottom is x times x squared, so that's x cubed. That means the degree on top is less, so we're all good. We don't need to do long division. But if we see this x squared minus 2x minus 2, that's actually not reducible. I can't simplify that and factor that out any further. That's actually as factored as it can get. So when I try to integrate this, I'm going to try to set this up as a over x minus 1, my first term. And my second term is going to have an x squared minus 2x minus 2 on the bottom. But since the highest degree on the bottom now is x squared, the highest degree on the bottom is going to be an x. So I'm not just going to have b, I'm going to have bx, and I need to continue and decrease down until I have a constant. So the top should be a polynomial with the highest degree of 1. All right. Now, even though that's the case, that's fine. We can still solve this. Because if you notice, we have x squared on the bottom, we have an x on top. So when we find what b and c are, we're still going to try to set this up as a natural log. Because I still have the degree on the bottom is 1 less than the degree on top. Or is 1 higher than the degree on top. Okay, so multiply each of these fractions by the denominator of the other side. So we get a. The x minus 1s are going to cancel, and we'll have a times x squared minus 2x minus 2. And then we have bx plus c times x minus 1 because the other trinomial will cancel out. And this we're going to set equal to the original numerator of x plus 7. All right, so we have a little bit of work to do. for the first one, let's multiply this all out so maybe it's a little bit easier to see, particularly when I have this term. It's not as easy as the last one where I could just combine nicely. I'll say ax squared minus 2ax minus 2a. Then I'm going to have bx times x will give me plus bx squared. Bx minus 1 will give me minus bx. C times x will give me cx. And c minus 1 will give me minus c equals x plus 7. So now let's group my terms. I have x squared on top here, so I will group some amount of x squareds. I have a and b as my x squared coefficients. My coefficients on the x terms are going to be minus 2a, and also minus b, and plus c. Those are my coefficients on x. Then my constant terms, I have a minus 2a and a minus c. So minus 2a minus c. That will equal x plus 7. Therefore, I have a few system of equations. Notice that since I have x plus 7, I technically have 0x squared plus x plus 7. There's no x squareds here, so that means I should set a plus b equal to x, or equal to 0 rather. I also have minus 2a minus b plus c equals 1, because that's the coefficient on x on the right side there. And for my constant that adds up to 7, I have minus 2a minus c. Move this up a little bit. A plus b. All right, so that's my system of equations that I'm going to use here. Now, when you have your system of equations, there's many different ways to approach this. I see this as, I see a minus 2a minus c, and so what I'm going to do is I'm going to use the top two equations to make another equation that only involves a and c, so I can start to eliminate from there. So what I'm going to do is I'm going to take the minus 2a minus b plus c, and what I'm going to do is simply add my top function of a plus b and no c equals 0, because if I add this together, I will cancel out the b's. I'll have minus b plus b is 0 b's. Minus 2a plus a will give me minus a, and c plus nothing will give me c equals 1. Put that together with minus 2a minus c equals 7. I can simply add the new one I just got, because negative a plus c equals 1 will cancel out the c's. So minus c plus c will give me 0 c's. Minus 2a minus a will give me minus 3a. And on the other side, I get 7 plus 1 is 8. So I don't get as nice of a number here. If I divide that negative 3 over, we get overall, if I write this down here, a equals negative 8/3, which I'll keep track of again over here. A, B, and C, we're looking for all three of these. A we got is negative 8/3. Now that we got A, we can solve for any of the other ones. I'll use the minus A plus C equals 1 because that looked easy. So minus A plus C equals 1. Plug in A, which is negative 8/3, plus C equals 1. That'll be a positive 8/3. Subtract to the other side. So we get C equals 1 minus 8/3. So that's 3/3 minus 8/3 will give me C is negative 5/3. And then I can solve B. Looking up, I have the easiest one possible. I have A plus B equals 0. And since I already know A is negative 8/3, I can add 8/3 and I get simply B is 8/3 itself. Alright, so not the simplest, but it's fine. That will allow me now to take my integral of x plus 7 over x minus 1, x squared minus 2x minus 2 dx. And now I can write this. Notice that all of them have thirds. All A, B, and C have thirds. So what I'm going to do is take out a third out of that. I'll do that in a moment, actually. This was split up into x minus 1, and on top was a, which is negative 8/3. Then plus the x squared minus 2x minus 2. On top I had bx, where b is 8/3, so 8/3 x. Plus c, where c is minus 5/3 dx. So now I could pull out a 1/3 out of this and make this just negative 8 over x minus 1 plus 8x minus 5 over x squared minus 2x minus 2 dx. Okay, now the first part is nice and easy. I can solve this by just doing a natural log. The second part's a little bit trickier. The way that I recommend dealing with the second part here is by completing the square, specifically completing the square on the bottom. So to do that, what I'm going to do is say, all right, ax minus, or 8x minus 5 over x squared minus 2x minus 2. What I'm going to do, I'll solve the initial 1/3, or negative 8/3 really. Natural log of x minus 1. And then for the rest of this, which is also a 1/3, I'm going to take the bottom, 8x minus 5. I'm going to take the bottom of x squared minus 2x. And what I want to do is add an amount that would be half of that squared. So minus 2 divided by 2 is negative 1 squared, will give me positive 1. Now, since I added a 1, I also need to subtract a 1 for compensation. That will allow me to say this is 8x minus 5 over this x squared minus 2x plus 1 simplifies to x minus 1 squared minus 3 dx. Okay, now what I do is I do a little bit of u substitution, and then I'm going to split up this. So I'm going to say u is equal to x minus 1, and if I set u to be x minus 1, that means as well that u plus 1 equals x by just adding that 1 over. And likewise, du equals dx. All those pieces will allow me to change this up. On top, I have 8x minus 5. I'm going to replace x with u plus 1. So I get 8u, and 8 times 1 will give me 8, minus 5 will also give me a plus 3. And on the bottom, I get u squared minus 3 du. All right. Then I can split up this fraction into two pieces. I could say 8u over u squared minus 3 plus 3 over u squared minus 3 du. Reason I split this up into two pieces and why I'm doing this is because there's not a simple u du from just the bottom and the top, unfortunately. So we have to maneuver this a little bit. On top, on the first one now, this I can do a u du, or I guess a w dw in this case. I can say that for that one, I could say w equals u squared minus 3, dw is 2u du. And that's how I can solve that one. That 2 I can divide to the other side, so that will become 4w on top, really. Or I'll just have a 4 left over on top, rather. So that will give me 4/3 natural log of u squared minus 3. And then for the last one, the plus 3u squared minus 3, that actually is one of the forms that we can use from the back of the book if we so please. From the back of the book, we have anything over u squared minus 3, that can be a system of natural logs. And what this will look like is plus 3 over 2 square roots of 3 natural log of u minus root 3 and u plus root 3 plus c. Lastly, need to replace all the u's back with x, 4/3 natural log. So u was x minus 1, so that's x minus 1 squared minus 3, which we know results in x squared minus 2x minus 2. That was our original. And then plus 3 over 2 root 3 natural log. In this case, I'm just going to keep it easy. I'm going to keep it x minus 1 minus root 3. And the bottom, x minus 1 plus root 3 plus c. Real quick, forgot that 1/3 to apply to this one, so that actually should not be a 3 on top here. That should be a 1. All right, that's pretty good. The only other thing I would do is maybe rationalize this. So instead of 1 over 2 root 3, I would keep this as root 3 over 2 times 3, which is 6. So root 3 over 6, and that's about it. That's the only other fix I would do, is rationalize that a bit. All right, that would be our partial fraction decomposition. So, bit of a long problem. These problems aren't going to be the shortest, although, again, I think over half this page was dedicated to simplifying what a, b, and c were. And then doing the integral took a little bit of extra work because we had that x squared, but that tends to happen when you have ones that you cannot decompose. With that said, that's everything for this section. If you have any questions, feel free to put them in the comments below or ask your instructor directly. I hope that you have a nice day.